Something appeared in the data that had no right to be there. It was August 2024. A team of astronomers at Caltech and NASA's Jet Propulsion Laboratory was processing the most technically demanding observation ever attempted by the James Webb Space Telescope, an observation so difficult that the telescope's own operations team had spent years developing a custom procedure just to make it possible. The target was not a distant galaxy, not a nebula millions of light years away, not a black hole shredding a star on the other side of the Milky Way. The target was our neighbor, the star closest in nature to our own sun, a star that had been studied for generations, that sailors had used for navigation for centuries, that every serious plan for humanity's expansion beyond this solar system treated as the first waypoint. Now, the target was Alpha Centauri A, and when the data came back, there was something there that had never been seen before. A faint point of light, more than 10,000 times fainter than the star itself, nestled beside it at approximately twice the Earth-Sun distance. Aniket Sanghi, a PhD student at Caltech and one of the scientists who found it, described his reaction with the specific honesty that only someone who has been fooled before by instrument artifacts can muster. He said it simply. It just popped out so clearly. He didn't want to believe it. He ran every test he could conceive to explain it away. He checked whether it was stray light scattered within the telescope's optics. He checked whether it was a background galaxy at a different distance. He checked whether it was a foreground asteroid drifting through the field of view. And he checked for every category of false positive he knew. His colleague Charles Beichmann, the astronomer at NASA's Jet Propulsion Laboratory, who had been the driving force behind this observation since 2017, had spent years being told it couldn't be done. The telescope was never meant to look at a star this bright, moving this fast, located in the middle of the galactic plane where thousands of background stars complicated every frame. When Beichmann had first proposed the idea in a 2017 email to colleagues, he had prefaced it with, "When you stop laughing, let's think about doing this project." Nobody was laughing now. The object was real. Or at least, it was something real, a genuine point source, surviving every test, sitting in the habitable zone of the nearest sun-like star to Earth. And then they looked again in February 2025. And it was gone. They looked in April 2025, still gone. "We are faced with the case of a disappearing planet," Sanghi said. And that sentence, 7 words spoken by a doctoral student processing data in a California laboratory, may turn out to be one of the most consequential sentences spoken in the history of planetary astronomy. Not because the planet is confirmed, it is not. Not because the discovery is certain, it is not. But because what it represents, what the combination of an appearance and a disappearance from the world's most powerful telescope says about the system closest to our own, the system that every human being who has ever looked up at the southern sky has seen as a single point of brilliant light, is a question that will not be answered quickly and that will not stop mattering until it is. Now, to understand why this discovery is extraordinary, you need to understand why it almost never happened at all. And to understand that, you need to understand the specific paradox at the heart of observing our nearest stellar neighbor. Alpha Centauri is the nearest star system to our sun. That proximity is both its greatest asset and its greatest observational liability. It is close enough that any planets orbiting it would be the easiest in the universe to study in detail, the closest candidate worlds that could conceivably be explored by robotic probes within the lifetimes of people alive today, the closest potential habitable environments that the human species could imagine reaching. The proximity makes Alpha Centauri the most scientifically valuable planetary hunting ground in the universe. And the proximity makes it nearly impossible to observe with a telescope optimized for deep space. The James Webb Space Telescope was designed and built to detect the light of the first galaxies formed after the Big Bang, objects 13 billion light-years away, so faint that every photon reaching the mirror is precious. Its detectors are extraordinarily sensitive. Its mirror, 6.5 meters in diameter, collects light with a hunger calibrated for extreme faintness. These capabilities are precisely wrong for Alpha Centauri A, which is the third brightest star in the entire night sky. Pointing JWST at Alpha Centauri A without protection would overwhelm its sensitive instruments instantly. Yet the way pointing a telescope designed to detect the light of a birthday candle a mile away would be overwhelmed by a searchlight held directly in front of the lens. The solution is the coronagraph, a specialized device within the MIRI instrument that functions as an artificial eclipse, using a precisely engineered opaque mask to block the star's light before it reaches the detector. Coronagraphs allow astronomers to study the faint environments immediately surrounding bright stars. They are designed for exactly this purpose. But Alpha Centauri A is not a single star. It is the primary component of a binary pair. Alpha Centauri B, its companion, nearly as massive and nearly as bright, orbits it at separations ranging from 11 to 36 astronomical units over an 80-year orbital cycle. When you block Alpha Centauri A's direct light with the coronagraph mask, the light from Alpha Centauri B continues to scatter across the detector field, illuminating regions where a planet around A might be found and creating a forest of false signals that must be painstakingly subtracted using computational models. Beyond Alpha Centauri B, there is the galactic background. The Alpha Centauri system sits in the direction of the galactic plane, the band of the Milky Way richest in stars, as seen from Earth. Behind the binary pair, thousands of background stars lie at various distances, each one capable of appearing as a false planetary signal if its light scatters into the instrument at the wrong angle or wrong intensity. Every possible false positive must be evaluated, modeled, subtracted, and dismissed before any remaining signal can be considered real. Then there is the motion. Alpha Centauri is moving across the sky at a speed unusually high for a star because it is so close to us. The parallax and proper motion of a nearby star are much larger than for a distant one. As the telescope tracks Alpha Centauri A, it must continuously adjust its pointing to follow the star's motion relative to the background, and it must do so with the coronagraph mask precisely centered on the target star at all times. If the star drifts even slightly off the mask center, the direct starlight floods the detector and ruins the observation. Yet, the operations team at the Space Telescope Science Institute in Baltimore had to develop a custom observing sequence, a procedure that had never been used for any other target in the telescope's history, specifically to handle the motion of Alpha Centauri during observations. The team attempted the observation in 2023. The data was unusable. The custom sequence wasn't yet right. They refined the procedure. They attempted again in August 2024. This time, it worked. And in the processed data, after the light of Alpha Centauri A had been blocked and the scattered light of Alpha Centauri B had been subtracted and the galaxy background had been modeled and removed, the faint point source was there. S1, sitting at approximately twice the Earth-Sun distance from Alpha Centauri A, consistent in its brightness and color in the mid-infrared. With a gas giant roughly the mass of Saturn, the implications were immediate and significant. If S1 is a real planet, it would be the nearest planet ever directly imaged in the habitable zone of a sun-like star. The nearest gas giant of comparable temperature and age to the giant planets of our own solar system. The nearest system beyond our own with a planetary architecture that could, depending on what else orbits there and what satellites the giant might harbor, be relevant to the question of life. But first, the disappearance. When the follow-up observations came back in February and April 2025 with no sign of S1, the team didn't panic. They simulated. Millions of simulations running on computing clusters in California, calculating the range of stable orbital paths that could account for both the August 2024 detection and the two subsequent non-detections. The simulations needed to incorporate not just Newtonian orbital mechanics, but the gravitational influence of Alpha Centauri B, whose presence perturbs the orbital environment around Alpha Centauri A in complex ways, defining a set of stable orbits that differ significantly from the stable orbits around a single star. The region immediately around Alpha Centauri A is gravitationally challenged. When two stars orbit each other at the separations of A and B, the planets of each star are restricted to orbits close to their host. Outside a certain distance, the gravitational pull of the companion star destabilizes orbits and throws planets into the void. The stable zone around Alpha Centauri A extends to approximately 2 to 3 astronomical units under the most optimistic assumptions. Beyond that, orbits become chaotic. Any planet detected at approximately twice the Earth-Sun distance is right at the edge of the orbital stability region, surviving by the narrow margin of a dynamic balance maintained over billions of years against the persistent gravitational influence of a stellar companion. The existence of S1 in this zone, if confirmed, would challenge existing models of planet formation in binary systems. The standard picture of planet formation, a protoplanetary disk of gas and dust orbiting a young star, gradually accreting into first planetesimals, then protoplanets, then planets, is complicated by the presence of a companion star. Thus, gravitational perturbations from the companion excite the orbits of material in the disk, increasing collision velocities to levels that inhibit accretion rather than promote it. The competing gravitational pull can truncate the disk, limiting the total mass available for planet building. Models suggest that forming a gas giant in the habitable zone of Alpha Centauri A should be significantly harder than forming one at the same location around an isolated star. And yet, S1 appears to be exactly that. Sanghi himself noted the significance. Its very existence in a system of two closely separated stars challenges our understanding of how planets form, survive, and evolve in chaotic environments. It is a statement as much about what we don't know as about what we found. The orbital simulations produced a partial answer to the disappearance. They found that in approximately 52% of all stable orbital solutions, consistent with both the August 2024 detection and the two 2025 non-detections, the planet would have moved into a configuration in early 2025 that placed it too close to Alpha Centauri A to be separated from the star by the coronagraph. The minimum working angle of JWST's MIRI coronagraph, the smallest angular separation at which the instrument can reliably distinguish a faint companion from the residual scattered light of the star, means that a planet that has moved close to its star in its orbital cycle would be hidden, not because it has vanished, but because it cannot be isolated from the star's glare at that particular point in its elliptical path. The disappearance is not, in the most probable orbital models, evidence that S1 is not a planet. Yet it is evidence that the planet is on an elliptical orbit that brings it close to the star, and therefore into the coronagraph's blind spot for part of its year. This is exactly what an eccentric orbit around Alpha Centauri A would produce. An eccentricity in planetary orbits is expected and frequently observed. The planet is not gone. According to the models, it is simply hiding behind the glare. The test of this interpretation is August 2026. The orbital solutions consistent with S1's observed trajectory predict that the planet should have returned to a position separable from the star by mid-2026. If the planet is real and the orbital models are correct, JWST observations in August 2026 should detect S1 again, at the predicted position, at the predicted brightness. Now, consistent with the combined orbital solution that incorporates both the 2019 VLT hint, the 2024 JWST detection, and the 2025 non-detections. There is also a prior detection to consider, which adds a dimension to the story that makes it simultaneously more compelling and more complex. In 2019, a team of astronomers using the Very Large Telescope at the European Southern Observatory in Chile detected a candidate object near Alpha Centauri A using the NEAR experiment, a specialized coronagraph installed on the VLT specifically for this purpose, using thermal infrared imaging at different wavelengths than the JWST/MIRI observations. The object, designated C1, was positioned at an angular separation from Alpha Centauri A consistent with an orbital distance of approximately 1 to 2 astronomical units. The detection was intriguing, but not definitive. The VLT is smaller than JWST, and the thermal infrared imaging at the relevant wavelengths is less sensitive than MIRI, and the signal could not be confirmed at sufficient significance to claim a planetary detection. But now there is S1, and the angular position of S1 in August 2024 is consistent within the measurement uncertainties of both instruments, with the position that C1 would have moved to by the time of the JWST observation, if both detections are of the same object, which has been moving through its orbit in the years between the two observations. The orbital solutions that treat S1 and C1 as the same object What the team calls the S1 plus C1 candidate tightened the orbital constraints significantly. They suggest an object on an elliptical orbit with a semi-major axis of approximately 1.1 astronomical units, an eccentricity of approximately 0.1 to 0.4, and an orbital period of roughly 1 to 2 Earth years. The temperature and brightness of this object, for a planet of Saturn's mass at this orbital distance from Alpha Centauri A, is consistent with what JWST detected. This is not a confirmed planet. The paper itself uses the word candidate carefully throughout. The specific language of both papers in the Astrophysical Journal Letters, accepted in August 2025, is deliberately restrained. They describe a candidate gas giant. They describe an object that cannot be unambiguously confirmed without additional observations. They describe the disappearance without claiming it as definitive orbital evidence. The language is the language of scientific humility, the language of researchers who know that the history of exoplanet science is littered with tantalizing hints that did not survive follow-up. And yet, Charles Bachman, the scientist who sent the laughing email in 2017, called the system the most valuable observational opportunity in the universe for learning about exoplanets. If confirmed, he said, this object would become a touchstone for exoplanet science, with multiple opportunities for detailed characterization by Webb and other observatories. A touchstone, a reference point, the nearest exoplanet in the habitable zone of the nearest sun-like star. A world, or at least a giant in whose gravitational sphere potentially habitable moons might orbit, positioned at 4.37 light-years. Thus, the implications extend beyond the immediate discovery. The scientific significance of S1, if it is real, spans multiple disciplines. For planetary formation theory, its existence in a binary system at the edge of gravitational stability challenges current models and suggests that the conditions for planet formation in binary systems are more permissive than theory predicts. Every confirmed planet in a binary system is a data point that either validates or constrains models of disk formation, truncation, and accretion. A Saturn mass giant at 1 to 2 astronomical units around Alpha Centauri A would be the most constraining such data point ever obtained, simply because the system is so well characterized and so close that every physical parameter, stellar mass, luminosity, age, metallicity, binary separation, is known with extraordinary precision. But for astrobiology, the significance of a gas giant in the habitable zone of Alpha Centauri A is more indirect but no less profound. Gas giants in habitable zones host moons. Jupiter has 4 large moons, 3 of which have subsurface oceans. Saturn has Enceladus, which erupts liquid water into space, and Titan, which has liquid methane lakes and a thick nitrogen atmosphere. If S1 is a real Saturn mass planet orbiting in the habitable zone of Alpha Centauri a sun-like star 6 billion years old, half again as old as our solar system, then whatever moons orbit S1 have been in a thermally favorable environment for 6 billion years, 1.5 billion years longer than life has existed on Earth. The biology of such moons, if any exists, would have had 1.5 billion additional years to develop beyond the most complex life that currently exists on this planet. We cannot see those moons. JWST cannot resolve individual moons around a planet that is itself only a single point of light. But the orbital position of S1, if confirmed, makes the existence of potentially habitable moons a physical possibility that 6 billion years of stellar evolution has had time to act upon. For the trajectory of future space missions, a confirmed planet at Alpha Centauri A would transform the target landscape. The Habitable Worlds Observatory, NASA's proposed flagship mission for the 2030s and 2040s, is designed to directly image Earth-sized planets around nearby sun-like stars. Alpha Centauri A is already on its target list, if S1 exists. And if the Ptolemy mission launching in 2026 detects an Earth mass wobble in Alpha Centauri A's position from additional smaller planets, the case for prioritizing the Alpha Centauri system in the HWO's survey becomes overwhelming. The system would be, simultaneously, the closest, the most accessible, and the most astronomically rich target available. The Nancy Grace Roman Space Telescope, currently in final preparation for launch no earlier than May 2027, carries a coronagraphic instrument specifically optimized for nearby star imaging. Roman's mirror is smaller than JWST's, but its coronagraph technology is more sophisticated for this specific application. After JWST's August 2026 observation either confirms or complicates the S1 story, Roman will be positioned to add its own independent data point, the third instrument. Now, after the VLT in 2019 and JWST in 2024, to have searched for planets around Alpha Centauri A with sufficient sensitivity to matter. 3 instruments, 3 time points, 7 years of data, and 1 question, still open, still pending its definitive answer. What appeared in August 2024 in the habitable zone of our nearest sun-like star and then disappeared in the spring of 2025? The most likely answer remains a planet, a Saturn mass gas giant on an elliptical orbit that brings it into JWST's blind spot for part of each orbital cycle. The orbital models support this, the brightness supports this. The consistency with the 2019 VLT hint supports this. The physics of the system, the stability zone, the binary constraints, the thermal signature, is consistent with this. But the universe has a way of being more interesting than the most likely answer. The history of planetary astronomy is a history of surprises. The first extrasolar planets discovered in the 1990s, massive gas giants in orbits tighter than Mercury's around their stars, violated every prior prediction about where planets should be found. The first terrestrial exoplanets were found around pulsars, the last place anyone would have looked. The first direct image of an exoplanet turned up a planet 4 times the mass of Jupiter in a star's outer disk. Every time the telescope has looked in a new direction with new sensitivity, something unexpected has appeared. One may be exactly what the models say it is, a Saturn mass gas giant in an elliptical habitable zone orbit, hidden by its star for part of each year, waiting to be confirmed in August 2026 when it swings back to a detectable position. Or it may be something else. Something the models don't yet have a category for. Something at the boundary of what the physics of binary stellar systems is expected to produce. Something whose existence, when fully understood, changes not just what we know about Alpha Centauri, but what we know about how planetary systems form and what environments can support the development of complexity. That is the nature of the frontier. The frontier is where the known gives way to the unknown. And the frontier is precisely where JWST has been operating since its first science observations. Finding things that don't fit expectations around distant galaxies, around exoplanet atmospheres, around the large-scale structure of the young universe. Yes, now it has found something that doesn't fully fit expectations around the star closest in nature to our own sun. August 2026 is the next chapter. JWST will look again. And whatever the data shows, whether S1 reappears at the predicted position, or whether the frame comes back clean and the puzzle deepens, or whether something entirely unexpected appears somewhere else in the field, the answer will bring us closer to knowing what orbits our nearest neighbor. The faint point of light that appeared in August 2024 and vanished in the spring of 2025 may be the first evidence of a world next door. A world that has been there for 6 billion years, orbiting the nearest sun-like star, illuminated by a star that is slightly warmer and slightly brighter than the one that illuminates Earth, in a system that has never been visited, never been measured up close, never been anything more to human beings than a point of light in the southern sky. Until now. Until JWST looked, and something popped out so clearly that even the skeptic who spent years running every test to explain it away found himself unable to explain it away. We are faced with the case of a disappearing planet, and the universe, as always, is waiting to see whether we have the persistence and the instruments to find it again. Let me take you deeper into the layers of this story because the surface account, telescope looks, finds something, loses it, will look again, leaves out the specific details that make each dimension of the discovery genuinely extraordinary rather than merely interesting. Begin with the people. Charles Beichmann has been one of the most persistent advocates for direct imaging of nearby stars for decades. His career spans the infrared astronomy community from the early days of IRAS, the infrared astronomical satellite, launched in 1983 and responsible for the first systematic survey of the infrared sky, through the Spitzer Space Telescope, through the Kepler mission's planet census, to his current position as executive director of the NASA Exoplanet Science Institute at Caltech. He is not a person given to impulsive claims. He is a person given to careful preparation of instruments and careful analysis of data. The fact that he spent 7 years from his 2017 email to the 2024 observation fighting for the technical development required to make this observation possible says something specific about the nature of the challenge. What he was fighting was not scientific skepticism about whether planets might exist around Alpha Centauri A. The scientific community widely expected planets to be there. The statistics of planetary formation around Sun-like stars, established by the Kepler mission's survey of hundreds of thousands of stars over 4 years, strongly suggest that most Sun-like stars harbor planetary systems. The resistance was more fundamental than that. It was the engineering community's informed assessment that the James Webb Space Telescope simply could not do what Bateman wanted to do. JWST was built with specific operational limits on how bright a target it could point at. These limits are not arbitrary bureaucratic rules. They are consequences of the physics of the instrument. When the telescope points at a very bright star, because the light scattered within the optical system, from imperfections in the mirror surface, from diffraction around the mirror segments, from secondary scattering within the instrument, creates a halo of diffuse light surrounding the star's core. For most targets, this halo is faint compared to the objects being searched for. For Alpha Centauri A, the star is so bright that even the halo carries more photons than any planet would. The instrument was not designed to subtract a halo this large. The algorithms for removing scattered starlight had not been developed for targets at this brightness. The motion correction required to keep the coronagraph mask precisely centered on a fast-moving nearby star had not been programmed. The development work that made the 2024 observation possible was, in itself, a significant engineering achievement. The team worked with the operations staff at the Space Telescope Science Institute to develop a target acquisition sequence that accounted for the star's proper motion during the observation, keeping the coronagraph mask precisely aligned despite the star moving across the sky at a rate that would have blurred conventional observations. They developed post-processing algorithms specifically calibrated for the Alpha Centauri A scattered light environment, testing them on simulated data before applying them to the real observations. They defined a set of quality criteria that any candidate signal had to meet before being considered real. Thresholds designed to eliminate the known categories of false positive specific to this observing geometry. S1 met all of those thresholds. Now consider the specific question of what the object might be if it is not the most likely interpretation: a Saturn mass gas giant in an elliptical habitable zone orbit. One alternative interpretation is that S1 is a background star caught at the right angular separation from Alpha Centauri A. The galactic background behind Alpha Centauri is rich in stars, and any one of them could potentially appear at the right position and brightness to mimic a companion. The team specifically tested for this. They examined the position of S1 relative to the background star field and checked whether any known catalog source was at the right position. They also compared the proper motion of the candidate, which, if it is a background star, should remain fixed relative to the background while Alpha Centauri A moves past it, with the expected position of a physically orbiting companion, which would move with the star. The August 2024 data point, compared with the 2019 VLTC-1 position, showed movement consistent with orbital motion around Alpha Centauri A rather than fixed background position. A background star explanation cannot easily account for both detections simultaneously. A second alternative is that S1 is a foreground object, a solar system body at a much smaller distance than Alpha Centauri A, perhaps a distant Kuiper belt object or Oort cloud comet that happened to pass through the small field of view during the observation. All this was also tested. The predicted motion of such an object would be dramatically different from the motion consistent with an Alpha Centauri companion, and the comparison with the 2019 VLT position rules out a slow-moving solar system body that far from the Sun. The most careful and complete analysis points persistently toward a bound companion. Something is orbiting Alpha Centauri A. The question is its nature, and here is the dimension of the story that transforms it from an interesting astronomical finding into something genuinely consequential for the next decade of planetary science. Alpha Centauri A. A is 6.1 billion years old. Our Sun is 4.6 billion years old. The difference, 1.5 billion years, is not trivial. Life emerged on Earth approximately 3.8 billion years ago, within the first billion years of the planet's existence. Complex multicellular life appeared approximately 600 million years ago. Tool-using intelligence appeared in the last few 100,000 years. Technological civilization in the last few hundred years. All of this happened in 4.6 billion years of solar system history. If a rocky planet exists in the habitable zone of Alpha Centauri A, and the existence of S1 does not preclude the existence of smaller companions. Ptolemy is specifically designed to look for them. It would have had 1.5 billion additional years of geological and biological opportunity compared to Earth. The chemistry of life, if it started on such a world at a similar point in the stellar lifetime as life started on Earth, would have had 5.3 billion years to develop. Complex multicellular organisms would have emerged, if the Earth timeline applies approximately 1.7 billion years ago on that world. The equivalent of our Cambrian explosion of animal diversity would have occurred 1.7 billion years before the present moment, and the equivalent of tool-using intelligence, if intelligence emerges on a similar timescale relative to complex life as it did on Earth, would have appeared roughly 1.5 billion years ago. A civilization 1.5 billion years more advanced than ours would be to us what we are to bacteria. Not merely more technologically capable, but so profoundly different in every relevant dimension. In its relationship to its physical environment, in its energy use, in its cognitive architecture if it retains cognitive architecture at all, that the concept of comparison loses meaning. Whether such a civilization would leave any signature detectable by our current instruments is genuinely unknown. Whether it still exists, or whether civilizational development has its own endpoint on timescales shorter than stellar lifetimes, is one of the deeper questions implicit in the Fermi paradox. But the specific scenario that most interests planetary scientists is not a hypothetical super-advanced civilization. It is the humbler and more immediate question of whether a rocky world in the habitable zone of Alpha Centauri A might harbor microbial life or complex life at stages comparable to Earth's Cambrian, or something in between. These possibilities are not detectably different from Earth at 4.37 light-years without instruments more powerful than any currently operational or planned. But the James Webb Space Telescope, with its extraordinary sensitivity in the mid-infrared, could in principle detect the thermal emission of a rocky planet in the habitable zone, not as a resolved disk, but as a point source superimposed on the stellar background, and obtain spectroscopic information about its atmospheric composition. The detection of biosignatures, molecular combinations in a planetary atmosphere that are difficult to produce without biological activity, such as the simultaneous presence of oxygen and methane, or the specific absorption features of phosphine or nitrous oxide, requires spectroscopic resolution and sensitivity that pushes JWST to or beyond its limits for a rocky planet at 4.37 light-years. But it is not physically impossible. Under optimal conditions, with multiple long observations stacked to increase signal-to-noise, some atmospheric information might be extractable for a rocky planet in the Alpha Centauri habitable zone. This is why S1 matters not just as a planetary detection, but as a roadmap. The confirmed existence of a giant planet in the habitable zone of Alpha Centauri A tells us that the system has planetary architecture. It tells us that planet formation proceeded around this star despite the gravitational perturbations of its binary companion. It tells us that the habitable zone, the region where rocky worlds with appropriate atmospheres could maintain liquid water, has been inhabited by something for 6 billion years, even if that something is a gas giant rather than a rocky world. And it opens the question of whether smaller, rockier companions exist at shorter orbital distances from the star, are protected from the destabilizing influence of S1's gravity by the specific dynamics of the system. The Ptolemy mission, The telescope for orbit, locus interferometric monitoring of our astronomical neighborhood, addresses exactly this question. Confirmed for 2026 launch, Ptolemy is a 16-unit CubeSat carrying a diffractive pupil lens that creates a complex interference pattern from the light of Alpha Centauri A and B. The lens acts as an extraordinarily precise astrometric ruler. By tracking the precise position of each star within the interference pattern over time, Ptolemy can detect the gravitational wobble that would be induced by a planet as small as a few Earth masses in the habitable zone. If Earth-mass planets exist in the Alpha Centauri system, Ptolemy find them. And if they do not exist at the sensitivity level Ptolemy can reach, the mission will establish that limit definitively and permanently. The convergence of these missions, JWST's August 2026 observation of S1, Ptolemy's ongoing astrometric search for Earth-mass worlds, the Roman Space Telescope's coronagraphic capability planned for nearby star surveys after its 2027 launch, and the longer-term horizon of the Habitable Worlds Observatory creates a scientific program centered on Alpha Centauri that is unprecedented in its specificity and its potential consequence. No other stellar system is the target of this many dedicated missions from this many different angles simultaneously. No other potential planetary system has this combination of proximity, stellar similarity to the Sun, age advantage, and now direct imaging evidence of a candidate planet. The scientific community, normally cautious about concentrating resources on a single target, has converged on Alpha Centauri with a focus that reflects its unique position at the intersection of every major line of inquiry in contemporary exoplanet science. And at the center of all of it, there is a question that does not require any philosophical sophistication to state clearly. Is there anyone there? Not almost certainly not, as the statistical rarity of technological intelligence would suggest. Not almost certainly yes, as the optimistic interpretation of the Drake equation might suggest. Just, is there anyone there? The question has been implicit in every human observation of that point of light in the southern sky, for as long as human beings have been capable of asking it. All ancient navigators used it to find their position on the ocean. Medieval astronomers measured its brightness and position. Modern astronomers have characterized its stellar properties to extraordinary precision. And now, for the first time in history, we have evidence of something orbiting it, something in the zone where, around our own sun, a world with oceans and an atmosphere and 4 billion years of biological history exists. The evidence is preliminary. The confirmation is pending. The full implications will not be known for years, possibly decades. But the question has entered a new phase, no longer purely theoretical, no longer dependent on statistical inference from distant stellar populations, no longer waiting for data. The data is here, a faint point of light in the processed images from the world's most powerful telescope. Found an object that popped out so clearly that even the scientist who found it ran every test he could conceive to explain it away. S1 is either a planet or it is something that every test applied to it says it probably is. The difference between those two statements is the word confirmation, and confirmation is coming. In August 2026, the James Webb Space Telescope will point its MIRI coronagraph at Alpha Centauri A one more time, using the procedure refined across 3 observation campaigns. And the data will either show a point source at the predicted position or it will not. If it shows the point source, the case of the disappearing planet will have become the case of the returning planet, and the nearest sun-like star will have become something different in human perception. Not just a bright point in the southern sky, yet not just a gravitational neighbor, not just a scientific target, but a system with a confirmed planetary architecture, a habitable zone with something in it, a place in the universe where the conditions for complexity have been operating for 6 billion years. If it does not show the point source, the mystery deepens. The absence of a redetection in August 2026 would be harder to explain than the absence in February and April 2025. The orbital models would need revision. The nature of S1 would need to be reconsidered, and the scientific community would be left with 2 separate detections, 5 years apart, of something real and unidentified in the habitable zone of our nearest stellar neighbor. Either outcome advances our understanding. Either outcome generates new questions. Either outcome is, in its specific way, a step forward in the longest and most important scientific project our species has ever undertaken, the search for whether we are alone. The case of the disappearing planet is one chapter in that project, not the final chapter, not even the most dramatic chapter, but possibly the chapter that, when it is read in retrospect from a future in which the question has been answered, will be recognized as the one where the evidence first crossed the threshold from theoretical to tangible. Something appeared in the data. It appeared beside our nearest sun-like star, in its habitable zone. And then it disappeared, and the universe is waiting to see whether we will look again. We will. In August 2026, the telescope is already being scheduled. There is one dimension of this discovery that I have not yet addressed, and it is the one that connects everything: the engineering triumph, the planetary detection, the disappearance, the orbital models, the 6 billion-year context, to the specific human experience of being alive at this precise moment in the history of our species. We are right now in the most compressed period of planetary discovery in human history. Before 1995, not a single planet outside our solar system had been confirmed. The first, 51 Pegasi b, a hot Jupiter orbiting a sun-like star 50 light-years away, was announced in October 1995 by Michel Mayor and Didier Queloz at the Geneva Observatory. It overturned almost every assumption about where planets could exist and what planetary systems could look like. Mayor and Queloz received the Nobel Prize in Physics in 2019. In the 30 years since 51 Pegasi b, we have confirmed more than 5,700 exoplanets. We have characterized the atmospheric chemistry of dozens of them. We have identified rocky super-Earths in the habitable zones of nearby stars. We have measured the temperature maps of gas giants. We have detected carbon dioxide, water vapor, methane, and sulfur dioxide in the atmospheres of planets orbiting other stars. The technology of planetary detection has advanced more in 30 years than in the preceding 4 centuries of telescopic astronomy. And in August 2024, that technology turned toward the star we have been looking at the longest, the nearest sun-like neighbor, and found, possibly tentatively, in need of confirmation but impossible to dismiss, a world in its habitable zone. The compression of this timeline is extraordinary. And the first exoplanet was confirmed the year that the Internet became publicly accessible. The JWST detection of a candidate planet at Alpha Centauri A occurred 29 years later. In those 29 years, humanity went from knowing of no planets beyond our solar system to having evidence, preliminary, pending confirmation, but evidence of a world in the habitable zone of the nearest sun-like star. Whatever the August 2026 observation reveals, the trajectory is clear. The instruments are improving. The techniques are being refined. The targets are being systematically eliminated or confirmed. Alpha Centauri A will not remain a mystery indefinitely. The combination of JWST, Ptolemy, Roman, and the Habitable Worlds Observatory will, within this century, either confirm or definitively rule out habitable zone planets in the nearest stellar system. The question will be answered. This is extraordinary. In the entire history of human inquiry, from the first philosopher who asked whether the stars were like our sun, from the first astronomer who measured the distance to the nearest star, from the first scientist who proposed that life might exist elsewhere in the universe, this question has been unanswerable. The nearest possibly inhabited system has been a point of light, beautiful and mysterious, and permanently beyond examination. And now, in this decade, the examination is happening. The faint smudge of light that Aniket Sanghi saw pop out of his processed data in August 2024 may be the beginning of the answer, not the answer itself, not confirmation of a habitable world or of life, or of anything beyond a candidate gas giant that is probably on an elliptical orbit that hid it from subsequent observations. But the beginning. Every great discovery in the history of science has had a beginning that looked to the person involved like something that might be something. Penzias and Wilson thought the noise in their antenna might be pigeon droppings. Fleming noticed that the mold contaminating his petri dish was killing the bacteria around it. Jansky realized the radio hiss he was tracking in his antenna wasn't interference from a thunderstorm, but something coming from a specific direction in the sky, the galactic center. In every case, the thing that changed history looked at first like something small, something that needed to be checked, something that might be an artifact. It just popped out so clearly. 7 words. A faint point of light, 10,000 times dimmer than the star beside it. An object that survived every test to explain it away. A candidate planet in the habitable zone of the nearest sun-like star that appeared in August 2024 and disappeared in the spring of 2025 and is predicted to reappear in August 2026. The telescope is being scheduled. We are waiting. And in the southern sky tonight, if you can find it, the brilliant white point of light near the Southern Cross, the third brightest star in the night sky, the one the ancient Arab astronomers called Ptolemy, the wine merchant. If you can find it, look at it for a moment. Not as an astronomical object, not as a navigational beacon, as a place, 4.37 light-years away. The light reaching your eyes left there 4 years and 4 months ago. In those 4 years, the observations were made, the data was processed, the candidate was found, the follow-up observations were run, the candidate disappeared, the orbital models were constructed, the papers were written and accepted and published, and the world is now waiting for August 2026. All of that happened while the light you are seeing now was already on its way. The light leaving that system right now will arrive here in 4 years and 4 months. By the time it arrives, the August 2026 observation will have been made and analyzed. We will know, or know more, about whether something real is there. And the light that carries the news of tonight's observation, the light that leaves JWST's detectors as photons encoded in data transmitted to Earth at radio frequencies. It's processed and analyzed and published in papers that will be read by astronomers who will point future telescopes at the same target. That information will propagate outward from Earth at the speed of light and arrive at Alpha Centauri 4.37 years from now. By then, we may know what S1 is. And whatever is there, if anything is there, will be receiving 4.37 years delayed, the light from this moment, from this search, from this question, we are looking, they will know. 4.37 years from now, they will know we looked.